Welcome to AI-driven perception, learning and mapping for drones. This is a lecture 8. It's part of a module foundational neural network where we talk about radial basis function. In the previous lecture we introduced feed-forward neural network. Particularly we talked about multi-layer perceptron and there is various parameters affecting the generalization capability including loss function. We are going to look at a new class of feed-forward neural network called radial basis function today. The outline of this particular module will start with what is radial basis function, what are the different basis functions one can use for this architecture. We present a single output radial basis function architecture and we take an examples of XR. If you remember XR problem is one of linearly inseparable problem. Can we revisit here? Can we use radial basis function to approximate the XR problem? Then we look at various learning approaches that is possible using radial basis function, right? And finally we see what is the difference between multi-layer perceptron and a radial basis function and that will give us flavor of different activation function based feed-forward neural network. And now what is this radial basis function? Now if you look at the response characteristics of a neuron in nervous systems, they are more local, right, or what we call locally tuned. These are classical experiments which is being done in neuroscience and understanding, and particularly when you look at the visual cortex, the responses are very local or locally tuned to the region of the input space, right. That is really opened up why our activation function should be in sigmoid or something, why can't be a locally tuned, right. Motivated by this experiment which was conducted on understanding visual cortex, how cells in visual nerve cells in visual cortex are responsive, right, to the local regions and in the eye, right. So that experiment motivated people to develop what we call radial basis function network. It is also one of the feed-forward neural network where the activation functions are local response, right, locally tuned responses. Famous Covers theorem states a complex pattern classification problem can be casted in a high dimensional space. Nonlinear high dimensional space is more likely to separate the data, it more likely to separate in linearly separable than in a lower dimensional space. We will explain that with the XR problem again. What we need to look at is if we project them into nonlinear space, the linear inseparable problem may become separable, right. We look at it when we take a simple, once we understand what is a radial basis function and we take a XR problem and revisit again, is a nonlinear projection is making it linearly separable or not. Okay. Now what is this single output radial basis function network? If you remember these x1, x2, xm in multi-layer perceptron we say these are the input features, they extracted information from the data and these are input, and you have a basis function here, right, in the hidden layer, single hidden layer network here, right. These are the radial basis function neurons. It takes the input, the inputs are directly fed to the neuron, unlike in MLP. In MLP what we do, we have a weights here. The weight scales the input. Here the weights are equal to 1, which means there is no change in the input which goes directly to the activation function. The output of the activation function are again multiplied by the weight, which again pass to output function active neuron, and we may have an activation function here and which will produce an output G, right, Y. Y is equal to G of whatever W into X is the activation potential is what we are talking here. So if you look at radial basis function, it has an input layer. The number of neuron in the layer corresponds to number of features that we have. It has an hidden layer one need to choose how many neurons should present in the hidden layer, and then you have an output layer. You can have more output neurons. I am just for the simplicity I am taking one output neuron so that one can understand. It can be n neurons also. And the weights connecting the hidden layer to output layers are W, and you have a special activation function which is a locally tuned. There are two parameters in activation function. One is the center, the other one is a variance. We will talk more about it in the subsequent slide. Right? Hidden layer employs locally tuned activation function. What does it mean? The response decreases with the distance from the neuron receptive field. It very local when the input is very close to the actual response. You can think of a bell in the temples, right? What happens at the center? It will give a maximum response. When you start moving away from the center, the response started decreasing, and when you are far away, it will become 0. That is a locally tuned function, right? Output layer can employ linear activation function, or you can have a nonlinear activation functions like MLP. For example, here we choose a linear activation function, right? What is this locally tuned activation function? What is this receptive neuron here, right? Here the hidden neuron uses something called radial basis function. The output of this hidden neuron depends on the current input data, which is x1 to xm, how the current input is away from the center of the receptive field. The center of the receptive field is represented as a mu, and the width or the variance of the receptive field, the width of the receptive field is represented by sigma. These two parameters control how the neuron responds to the input space, right? Mathematically, if I wanted to represent, phi is nothing but exponential activation function minus the distance between the sample x and a mu. Mu is an m dimensional vector. If the x is a m dimensional vector, mu is also an m dimensional vector, right? What is the Euclidean distance between the current sample and the receptive field? Square of that divided by 2 sigma square. Sigma is the width of the receptive field. This is the Gaussian function, right? As a kind of a radial basis function. Now, one need to understand what will happen if the sigma is larger and smaller, right? Now, if you look at it, the hidden neuron is sensitive to the data point nearest to its center, right? If your sample is closer to mu, it will produce a maximum output. If the sample is far away from this center, the output becomes 0, right? Now, let us say if sigma is 1, how does the distribution looks like? If the sigma is 0.5, how does the distribution changes, right? The width plays an important role. It is very sensitive to how the spreads are going to be. If the larger spread means lesser sensitivity, lesser spread means higher sensitivity. Biologically, if I want to talk about it, how a particular cells are tuned to a specific frequency is, right? That is how we see it here, right? Now, if I keep increasing the width, it becomes more flatter and flatter, right? So, if I have more spread, again this is how it looks like in the inputs feature space of x and y, right? Now, is that a only activation, only function which has the radial nature of it? There are many other functions one can use. Example, multi-quadratic, phi of r, right, where r is the activation value or input feature. If you are talking about r is nothing but the input feature x, then x square plus c square power 1 by 2 or square root of x square plus c square. It is like a multi-quadratic function. It is also radial. When x closer to z, it is 0, otherwise it will just keep increasing. Inverse multi-quadratic, if I just put it 1 by x, is something similar to your Gaussian function. When x and c's are closer, you have maximum, and away it becomes 0. You can have other spline, right? One could think of a thin plate spline, right? I can have wi phi x minus c. These are different activation functions which is having a characteristics of locally tuned response. Most commonly used is the Gaussian neural network, which has exponential minus x minus mu I by sigma square, right? That's the representation. So in this particular lecture we focus more on Gaussian function. For a simplicity, I am going to take a single output radial basis function. The input layer has m features. The hidden layer has L Gaussian neuron, and we have one output. I am assuming that I am going to employ a linear activation function y is nothing but w j phi j, right. So my hidden layer activation function response is represented by phi I. It depends on two parameter, mu I and sigma I. Mu I is nothing but center of the Gaussian function. The dimension of mu is nothing equal to dimension of the input space. Sigma I is a scalar quantity. It's a spread. It's a positive scalar quantity. Okay. So sigma is single value, right? Sigma is r power 1, whereas the mu is r power m. I am using a linear activation function. So y goes from j is equal to 1 to L, okay, wj phi j. So what is the objective here? Given a set of data, we need to find the parameters of the network such that it approximates the relationship between the input x and output y from a fixed finite set of observation, right. We need to find the parameter w, which is the weight connecting the hidden layer and output layer, the mu, right, this Gaussian center, and sigma, right. For there are L such values and your weight vector w. We have to determine this such that it approximates the input and output very well, right. Now let us revisit the XR problem. What we said, XR is linearly inseparable. The input space, if you look at, there are two inputs, right, x1 and x2, isn't it? The inputs are x1, x2. The input could be 0 or 1, right. What XR says? If 0 0, it belongs to the class 0. If it's 1 1, it is also 1. So there is no way I can draw a line to separate these classes. If I draw a line, this is a class 1, it comes into picture. If I draw a line also, it is very difficult. It's in the space of x1 and x2, this is linearly inseparable. So can we construct an RBF architecture such that these data can be classified? So what Cover's theorem says, when you are projecting the data in nonlinear dimensional space, higher dimensional space, it could be linearly separable, isn't it? So suppose if I take the data, okay, x1 and x2, x1 can be 0 or 1, there are 4 possible values, right. 0 0 means the target is 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. That is the input space and output space we are representing. So what is the problem here? There are 2 input, 1 output. I am creating 2 input, 1 output neuron, right. The output layer has a linear activation function, and this is the architecture I am trying to see. let us say somehow I find the mu and sigma. Okay, I gave mu being 1 comma 1 for one neuron, the first neuron center, right, the mu 1 is nothing but 1 comma 1. The mu 2, right, the center is 0 comma 0. Okay. Both neurons have the same spread 0.707. If I use this as an activation function, it's a nonlinear projection, right? The two dimensions being projection into phi 1 and phi 2. In that space, will it be linearly separable? That's a question we are asking, right? So let's try to map the data x1 and x2 into phi 1 and phi 2, right? This is my phi 1, this is my phi 2. In the space of phi 1 and phi 2, if it's linearly separable, then the theorem says if you project them into higher dimensional nonlinear space, that becomes linearly separable. We can verify that, right? So I take the data x1 and x2. If I compute phi 1, I get 1 comma 0.1353 for phi 2. For 0 and 1, I get 0.3678 and 0.3678. For 0, 0, I get 0.1353 and 1. You remember one of the neuron center, right? Mu 1 is 1 comma 1, mu 2 is 0 comma 0. When a sample is exactly falling on the center, it gives a maximum output, right? Whereas for 0 comma 0, 1 comma 1 is far away, hence the output is smaller. Whereas if you look at 1, 0, if you are giving, both the neurons gives more or less the same output because they are all almost equidistant because the spreads are same, right? Now if I am trying to draw the data in nonlinear space of phi 1 and phi 2, what happens? The sample 0 and 1 and 0 map to a single point in a phi 1 phi 2 space, right, which is close to 0.3678 and this, right. Whereas if you look at the data of 1 comma 1 and 0 comma 0, they are mapped to these points, right. Now you see I can draw a decision surface separating these, sorry. Suppose if I am mapping the data 0 comma 0 and 1 comma 1, they are mapped to the point here. Whereas we look at 0 comma 1 and 1 comma 0, they are mapped to the same point represented in orange. Now you see in phi 1 and phi 2 space, the XOR problem becomes linearly separable, which validates the Coase theorem, right. You can draw n number of decision plane which is linear, which can segregate this data, right. Projecting a data in higher dimensional nonlinear space, here we are not actually making it a higher dimension, but it's same 2-dimensional space, but it's a nonlinear projection. Moment we make the data in nonlinear projection, they are linearly separable. Now let's find the decision line which is passing through, right. What is my equation for output? Y. If you remember, Y varies from summation j is equal to 1 to L Wj phi j, right. Here L is equal to 2. If I am writing it, Y is equal to W naught, that is bias value, phi 1 W1, phi 2 W2, right. So for various values of x, x can be 0, 0, 0, 1, 1, 0 and 1, 1. If I substitute that, what I get corresponding phi 1, phi 2, right. I am assuming there is something called phi 3 which is bias, right. If you remember, how do we do bias? W naught is by bias, the input corresponding to it is 1. So there are 3 inputs, phi 1, phi 2 and the bias input. There are 3 weights, W1, W2 and W0, right. The targets are given, 0 0 belongs to 0, 0 1 is 1, right. Then we have 1 1 is 0, 1 0 is 1. So I am representing the classes like this. So I have to find out, right. I have to solve this system of linear equations to find my weight. How we will do it, we will just look at it in the next step. Somehow I found my weights are like this. Then I know the decision surface. I can represent the decision surface here, which maps the data, right, which finding the line which is passing through, right, which segregate the data x1 and x2, which is otherwise linearly inseparable. Because I am projecting it into phi 1 and phi 2, the space becomes linearly separable. Okay. So I substitute here, check whether it is true or not. When I give a data 1 comma 1, I have to get 0 as an output, but I am getting value very close to 0. When I give 0 and 1, I should get output as 1, I am getting 1.001, right. I can compute the error and see, right. So I can say that the network is able to approximate the XOR problem very well. Now the question, can I learn them, right, automatically? Here we fix, somehow I found out what is mu and sigma and what is my W. Can I learn them automatically? That is a question in front of us. There are various ways in which one can find it. Let us say what I can do, I have n observation samples. I decided to have h number of neurons, Gaussian neurons. I can randomly pick some h samples, assign them as my centers. Like if you look at previous case, I randomly picked 2 samples, 0 comma 0 and 1 comma 1, I made them as a center. One can do that. And you can compute the weight, sigma. How do you do it? You find out the maximum distance between any 2 centers divided by square root of total number of centers. So D max divided by root of k. K is number of centers. Here k is equal to h, right. So sorry, here you can say k, right. D max divided by square root of k. That is what I did. The maximum distance divided by 2 centers are there, square root of 2, which comes out to be 0.707. So I fix the center, I fix the width for all the neuron, then I just need to compute y. Y is nothing but W0, phi 1 W1, phi 2 W2, phi k Wk. So I am going to do and compute this weight, right. So by pseudo inverse, by equating y is equal to d. So how am I going to do? If I am going to represent them in matrix form, right, my phi 1, phi 2, so this is phi k, right. I am assuming there is no bias, I am ignoring W0 for a simplicity. If you want to do it, you just have to create 1 1 1 additionally, right. So this is my phi matrix. If you include a bias, the phi matrix will be phi 1 of x1 dot dot dot, phi k of x1 and 1 will be there. Similarly, phi 1 of xn, nth sample, the n represent the nth samples, phi k of xn and 1. This is your matrix, right. If you include the bias, you start with W1 all the way to Wn and you will have W0, sorry Wk and W0, which is equal to your D1 to Dn. Okay, if you include the bias. So let us say I am going to call G is a matrix which has all the responses of activation functions for all the observations. Then I can represent G or G times W is nothing but my D. G is a rectangular matrix. The one way to find, I multiply by G transpose on both sides. I am sorry. So if I do that, G transpose G W is equal to G transpose D. The G transpose G will become a square matrix, so I can get the inverse. So my W is G transpose G whole inverse G transpose into your D vector. That is your W. This is nothing but pseudo inverse of this matrix G, right. I can use pseudo inverse to compute my W straight away. If you look at our XOR problem, that is what I did. I randomly pick up two samples and that is the center of the Gaussian. I computed the maximum distance between any two center, right, and I use that maximum distance divided by square root of number of Gaussians, that is the sigma for all the neurons. Then I can use a pseudo inverse to do it. In this learning approach, the problem is if the choice of centers is not proper, then you will not be able to approximate the relationship, right. Why do we need to pick the samples as a center? Can we not learn them? Right? That is a question in front of us. Yes, you can do. One can use kind of a clustering technique. I randomly initialize the neurons, right. I draw m samples from the training data. I can try to find the similarity between the samples, whether the samples are, which samples are similar to that particular center. If the samples are similar to the center, then I am going to adjust the center towards the sample. Mu I is mu I plus eta times x minus mu j if the data is similar to that particular center. If the data is similar to some other center, that will get updated, otherwise it remains same. I keep doing it on my observation till the centers converges. Then that is my center. And I can use the center again, find the maximum width, and I can fix the width, and I can use the least square solution to get the solution. In this case, I am not fixing the center to the sample space, I am trying to find out the pseudo center of the distribution of samples closer to each other, and that becomes the center, and those classes are important. Now the issue is, how do I fix my number of neurons here, right. Once I have, the other way is like what we did in multilayer perceptron. We define the error. Let us say E is equal to 1 by 2 E square. What is the error here? Small e is nothing but D minus Y. I define the loss. The best way is I can do the gradient update, right. How do I find? Dou E by dou Wi. First I wanted to find the update rule for Wi. Dou E by dou Wi, if I am differentiating the E, 1 by 2 times 2 times dou E by dou Wi, small e, right. What is dou small e by dou Wi? Where error is D minus Y, D is the ground truth, Y is the predicted value. So you will get minus 1 times dou Y by dou Wi. What is Y? Y is nothing but summation I is equal to 0 to L Wi phi I. If you differentiate this is a linear activation function, dou Yi by dou Wi, rest of the term will become 0, you will get phi I. So what is my update rule? Dou E by dou Wi is nothing but dou E by dou small e times dou E by dou Y by dou Wi. If I substitute all the variables, what do you get? Minus E into phi I. Right? That's the change in weight that I could have. So what is the new weight? Wi is nothing but old weight plus eta times E into phi I. This eta is nothing but the learning rate. Negative gradients will take it, right? That's why I'm just become plus eta into E into phi I. Now same way I can do it for the center mu I, right? So if I'm trying to differentiate E, dou E by dou mu I is nothing but dou E by dou E, small e, dou E by dou Y, then you will have dou Y by dou phi I, because we are trying to find with respect to mu I, the corresponding phi I only will be needed, dou phi I by dou mu I. So we know from the previous derivation dou Y by dou phi I is Wi, because what is Y? Y is nothing but summation Wi phi I, right? So when you differentiate this, you will get Wi. When you differentiate dou phi I by dou mu I, right? So whatever dou of e power x is same, right? That is phi here, sorry, this is phi I times dou of the term inside, right? There is a negative here, sorry. The minus comes into picture, minus phi into this term, whatever the derivative there, then you will have mu I, this will become plus E by sigma I square and x minus mu I. So if I am going to substitute all of this, my update rate will depends on, right, minus 1 E Wi times whatever the gradient, right, phi by sigma I square and x minus mu. Similarly, I can do it for width, right? I can get the update rate. Sorry, this is not E, this is phi, okay. So if I am going to differentiate with respect to width sigma I, dou capital E by dou small e by dou y, and dou y by dou phi I by dou sigma I. So I am trying to derive that part. Dou phi I by dou sigma I is very important, rest of the things remain same. Exponential e power minus x is e power minus x, right. So that is a phi I you will get as it is. Dou by dou sigma I, the numerator remains same, and then I am just putting the denominator, so the numerator part will not change. So what you get, 1 by 2 sigma I square, right. So the 2 cancel, it becomes sigma I power minus 3, right. So that is what you will have. Now with that, what I can do, I can find out what is the change in weight for mu, change in center, change in sigma, change in weight. I can get the gradient descent update rule, right. What I do, first I compute the outputs, what is phi, what is y. I can compute the output phi and y, and I can compute the error. I compute the gradient delta w, delta mu and delta sigma, and then I can update w, mu and sigma and repeat this step till the convergence. We talked about different learning approaches for radial basis function network. We saw how we can initialize randomly some samples as a center and some sample as based on the samples we can compute the sigma and we can estimate the W. Later we saw why to pick randomly some sample, we can use clustering based approaches. One can also use gradient based update. For this you need to define error E, right, capital error, that is a loss function that we are defining. E, capital E is equal to 1 by 2 E square. I am just showing it for a single sample. and then one can generalize, right, similar to a multi-layer perceptron, where E is nothing but D minus Y. Y is my network output, D is my target, right. So what we wanted to update the output weight for Wi. So then we need to find out the gradient with respect to Wi, that is dou E by dou Wi. If I am differentiating with respect to that, what we will get 1 by 2, E square will become 2E, then you get dou E by dou Wi. This is small e, right. What is dou E by dou Wi? E is nothing but D minus Y, right. If I am differentiating that, D is a target which is constant. So minus Y you will have. So minus 1 into dou Y by dou Wi. What is my Y? Y is nothing but summation I is equal to 0 to L Wi phi I. Remember, W0 is nothing but bias weight, right. Phi 0 is 1. Okay. So with this, if I differentiate dou Y by dou Wi, I get phi I, right. So what is the gradient with respect to Wi? Dou capital E by dou Wi is dou capital E by dou E by dou Y, and dou Y by dou Wi. I am substituting all of this. What I will get? Dou E by dou Wi is E times minus 1 into phi I. What is the update rule? Old weight is equal to, new weight equal to old weight minus negative gradient. Eta is nothing but our learning rate, right. It's our step size, how we wanted to descend down, right. So if I substitute all of this, my update rule is nothing but eta times E times phi I. Phi I is input, E is the error. Now let's do the same thing for the center of a Gaussian, which is nothing but mu I, right. What is the update rule? Mu center is nothing but old center minus eta times the gradient, that is dou E by dou mu I. So if I look at dou E by dou mu I, dou capital E by dou E, dou small e by dou Y by dou phi by dou mu I, right. So we have derived already dou capital E by dou small e by dou Y. So I am not going to do this again. Let's focus on dou phi Y by dou phi I. Y is nothing but summation I is equal to 0 to L Wi phi I. When you differentiate this with respect to phi I, you will get only Wi. That's a term, right. Now let's focus on dou phi I by dou mu I. What is my phi I? Phi I is nothing but exponential minus x minus mu I whole square by 2 sigma I square. Remember, x is a vector, mu is also a vector, right. So dou phi I by dou mu I, if I am looking at e power minus x, if you differentiate you will get e power minus x itself, right. Then the whole term you will have minus and dou by dou mu I of x minus mu I by 2 sigma I square, right. If I am differentiating this, what will I get? Phi I by 2 sigma square 2 times x minus mu I into minus 1. So I can just cancel out. See, while deriving, I am not considering mu ij. I should have done it with respect to mu ij, and j varies from 1 to m. Okay. So I am just representing the vector notion straight away so that it is easier for us to appreciate, right. If I substitute this back, dou phi I by dou mu I, if I simplify, I will get phi I by sigma I square into x minus mu I, right. And dou phi I by dou mu I, the phi I is nothing but exponential e power minus x minus mu I whole square by sigma I square. If you substitute all of this, the gradient with respect to mu, it will be like this, right. Error times minus 1 times Wi phi I by sigma I square x minus mu I square, right. So if you substitute, the update rule is eta I mu center is old center plus learning rate times error times the corresponding weight. So if you look at, this is also similar to back propagate, right. this is my error, right? Error times Wi is the error contribution by this neuron into that activation function, because that is a derivative of the activation function, and x minus mu sigma I square. So, this is what the update rule, right? We do not know exact output of this Gaussian. If you know the true Gaussian value, we could directly compare and update. Here what we are doing with respect to error, we are propagating. Remember, we have taken for simplicity single input system, single output system, right? So, you can generalize when you have more error. Let us say this is E1, then you have E2, then the error contribution will be Wi1 and Wi2 will be there. This is E1 times E2. The error contribution by the neuron, output neuron 1 as well as output neuron 2, corresponding weight multiply will tell you what is the error contributed by the ith Gaussian neuron, right? It is exactly similar to our multilayer perceptron in terms of back propagation, right? Except there the activation function is either sigmoidal or bipolar sigmoidal. Here RBF has a very unique activation function which is locally tuned. So, here using Gaussian function, and that activation function derivative is what we need to use. Now, we will do the same thing for sigma I, right? In RBF neuron, mu I, sigma I and Wi are the parameters which we need to find the gradient, right. So, now we will find the gradient for the width sigma I. Sigma I is nothing but, update rule is sigma I minus eta times the gradient with respect to sigma I. Capital E is the loss function. So, if I am just trying to look at how we can compute the chain rule, dou E by dou sigma I is nothing but dou capital E by dou small e times dou small e into dou y by dou phi I and dou phi I by dou sigma I. Just to connect you back again, dou capital E by dou small e will have 1 by 2 into 2 times E, dou E by dou y you will have minus 1, right. Dou y by dou phi I you will have Wi, and we have to focus on phi I. Dou phi I by dou sigma I, right, e power minus x, right. If we differentiate, e power minus x is e power minus x itself into minus 1 you will have, and then dou by dou sigma I of the term x, which is nothing but x minus mu I whole square by 2 sigma I square, right. The numerator is independent of sigma I width. So, the numerator will come as it is. Then what we will have, dou by dou sigma I of 1 by 2 sigma I square, right. So, if you are differentiating that, you will get minus 2 divided by 2 sigma I cube. So, this minus 2 and this 2 will cancel, right. So, this minus and this minus is cancel. What you get is phi I times x minus mu I the whole square divided by sigma I cube, right. So, if you substitute this back into the chain rule, what you get, learning rate times error times Wi times the output of the Gaussian ith Gaussian multiplied by x minus mu I the whole square divided by sigma I cube, right. So, now I have gradient update rule for Wi, I have a gradient update rule for mu I have a gradient update rule for sigma I. So, what I can do, I can randomly initialize the center, the width, the number of Gaussian required, and the weight corresponds to the Gaussian and output. Then for every sample, I can find out the hidden layer output, which is phi, it is a vector, remember, and then I can compute the output y, I can compute the loss E, and I can compute the gradients for Wi, mu I and sigma I, and then I can update for that particular sample, repeat for the next sample. I can keep repeating it till all the samples are in the training data is presented, and again start from the first, do it again till convergence. Or what I can do, I can use block of samples. For a given batch of samples, I can compute phi and y, I can compute the error, I can compute the gradient and update. Okay. Now, what is the difference between multilayer perceptron and radial basis function network? If I had to compare, right? I can compare them based on layer, based on the activation function, based on the output layer activation function, and based on the operation that it is trying to perform, what kind of problem nature that it is trying to address, right? If you look at a layer, RBFN has a single hidden layer, whereas MLP has many layers. Again, is that the limitation? Then I can invoke universal approximation theorem. Any function, smooth and continuous function, can be approximated with a single hidden layer network with a large number of hidden neuron. I can approximate it. Okay. Now, what is the activation function used in RBF? Locally tuned. We saw a different type of activation function one can employ, which has a locally tuned characteristics, right? When the input sample is closer to the center, it gives a maximum output. When it's moving away from the center, the output exponentially decay to 0. Whereas if you look at multilayer perceptron, you can use any general function. We saw what kind of activation function possible. Linear, right? Sigmoidal, unipolar, bipolar, right? And any function, general function, can be used as an activation function. In the output layer, in RBFN has a linear activation function, whereas multilayer perceptron, it could be linear or nonlinear. You can do both, right? If I look at the operation aspect of it, radial basis function network activation uses Euclidean norm, whereas multilayer perceptron uses the inner product between the weight and the input, right? That is a key. If you look at the nature, RBF is used for exponentially decaying localized nonlinearity to approximate the input-output mapping, whereas MLP is a global approximator. That is a point you need to understand. We prefer multilayer perceptron when we talk about continual learning aspect of it or online learning aspect of it. When the data is not available a priori, right? Data is evolving over a period of time. It's very difficult to use multilayer perceptron to approximate the relationship, right? Because you have to represent the data again and again. But if you use a locally tuned function, the newly arrived data is far away from existing Gaussian. I can simply add a neuron around that particular data so that it can approximate the local region very efficiently. That's the reason, if you see the literature, people use radial basis function network for evolving our architecture, right? What I meant evolving is I can always start with 0 hidden neuron. The first sample could be the first center. And then I can just look at the error and decide whether to add a neuron or update the weight, right? So you can evolve the architecture based on the data it arrives. You can also delete neurons. If some neurons are inactive for a long time, you can delete, right? So that's the reason locally tuned functions are most suitable for evolving neural network. Okay? You can't do this with MLP because it's an inner product, right? All neurons will produce some output, okay, unlike locally tuned activation function. So in a sense, this particular lecture introduced a new architecture called radial basis function network, which uses a locally tuned nature of activation function. We talked about different function which has a similar characteristics, and then we constructed a single layer radial basis function neural network, feed-forward neural network, and we demonstrated the Cover's theorem using single layer neural network, how one can use projecting the data into nonlinear space. In the nonlinear space it becomes linearly separable. In this case XOR problem we have taken. In input space is not separable. When we project the input space into phi 1 and phi 2 and then we can find a line to separate, we demonstrated that. Then we looked at different learning approaches available for radial basis function network, starting from random initialization with the pseudo inverse. You can pick the samples randomly and the samples becomes a center, and then you fix the sigma constant based on the maximum distance between the centers, and then you can compute the pseudo inverse. The pseudo inverse will just give you the output weight. Remember, if the data you have selected randomly, if it is not representing the entire distribution, then the convergence becomes bigger issue. Generalization performance of the network becomes an issue. Then why randomly pick up sample? Why can't I use clustering approach, find naturally how many clusters being present and use that cluster center as the center of the neuron, and I can find out the maximum width. I can fix it, or I can use the cluster center itself and the distribution of the cluster to find out the sigma, and I can use pseudo inverse again. Then we talked about gradient update. We all know initialization is the biggest key. Initial weights, right? If you randomly pick the weight and the weights are nowhere nearby, then the output from a Gaussian will be very small, which means the error is very high. The changes in W will be significant and which will in turn affect the convergence of the network. One can use either clustering based approach to initialize the center and width and pseudo inverse to compute the weight, and once you use this as an initial network, fine tune it further using gradient descent update, right? We can employ any of this. And also we discuss about the difference between MLP and RBF. Remember, one big advantage using radial basis function network is evolving architecture or online learning. The data coming as a stream, I can learn from the data and the data will not be presented again, which means I don't have to store the training data, right? That's the biggest advantage using radial basis function network. Whereas MLP is a general approximator, right? RBF has, because of special function, we know what is its limitation and you need to understand. For a given problem, if one need to use a shallow neural network, he need to think through what is the architecture, how many neurons required, how many layers required, what kind of activation function we should choose, what is the loss function we should have, how do we initialize the data, do we need to normalize the data. If it gets stuck in a local minima, we should know we should either employ momentum term to accelerate, right? Or we have to have a regularization mechanism so that the convergence become better. Thank you.